Hello and welcome back at the FinetLink channel where we are going with the second video about LAN security concept. At the first video we explained how to use endpoint security to mitigate attacks, and we will explain the AAA and the security that are used to authenticate LAN endpoints and devices. And now in this video, we will identify layer 2 vulnerabilities, and we will explain how a MAC address table attack compromised LAN security, and then we will explain how LAN attacks compromise LAN security. In the video, we discussed securing endpoints. And now we will continue to learn about ways to secure the LANs by focusing on the frames found in the data link layer and the switch. By recalling that the OSI reference model is divided into 7 layers which work independently of each other. Here in this figure, it is shown the function of each layer and core element that can be exploited. Network administrators routinely implement security solutions to protect the elements in layer 3 up through the layer 7. They use VPNs, firewall, IPS devices to protect these elements. However, if layer 2 is compromised, then all the layers above are also affected. For example, if a threat actor with access to the internal network captured layer 2 frames, then all the security implemented on the layers above would be useless. The threat actor could cause a lot of damage on layer 2 LAN networking infrastructure. Security is only as strong as the weakest link in the system, and layer 2 is considered to be the weakest link. This is because LANs were traditionally under the administrative control of a single organization. We inherently trusted all persons and devices connected to our LAN. But today, with bring your own devices and more sophisticated attacks, our LANs have become more vulnerable to penetration. Therefore, in addition to protect layer 3 to layer 7, network security professionals must also mitigate attacks to the layer 2 LAN infrastructure. The first step in mitigating attacks on the layer 2 infrastructure is to understand the underlying operation of layer 2 and the threat posed by the layer 2 infrastructure. Attacks against the layer 2 LAN infrastructure are described here in this table and we will be discussed later in this video. So we have MAC table attacks, VLAN attacks, DHCP attacks, ARP attacks, address spoofing attacks, and STP attacks. And it is explained for each of the attacks what does it includes during the attack. And here in this second table, we provide an overview of Cisco solution to help mitigate layer 2 attacks. How can you do that? By using the port security, by DHCP snooping, by dynamic ARP inspection, and by IP source guard. And for each of those solutions, it is explained in which case we will need it and how you will do it. This layer 2 solution will not be effective if the management protocols are not secure. For example, the management protocol syslogs, Simple Network Management Protocol, Tribal File Transfer Protocol, Telnet File Transfer Protocol, and most other common protocols are insecure. That's why we'll need strategies to secure them, which means always use secure variants of these protocols, such as Secure Shell, Secure Copy Protocol, Secure FTP, Secure Socket Layer, Transport Layer Security. We always have to consider using out-of-band management network to manage devices. We use a dedicated management VLAN where nothing but management traffic resides. We will even use access lists to filter unwanted access. So let's go now and see those MAC address table attacks, which means that we will focus still on switches, specifically at their MAC address table and how these tables are vulnerable to attacks. By recalling to make forwarding decision, a layer 2 LAN switch builds a table based on the source MAC addresses received by frames. Here it is shown what is called a MAC address table. The MAC address tables are stored in a memory and are used to more efficiently forward frames. All MAC address tables have a fixed size and consequently, a switch can run out of resources in which to store MAC addresses. MAC address flooding attacks take advantage of this limitation by bombarding the switch with fake source MAC address until the switch MAC address table is full. When this occurs, the switch threads the frame as an unknown unicast and begins to flood all incoming traffic out of port on the same VLAN without referencing the MAC address table. This condition now allows a threat actor to capture all the frames sent from one host to another on the local LAN or local VLAN. And remember that traffic is flooded only within the local LAN or VLAN. The threat actor can only capture traffic within the local LAN or VLAN to which the threat actor is connected. And here in this figure, it is shown how a threat actor can easily use the network attack tool MAC-off to overflow a MAC address table. How it works. The threat actor is connected to the VLAN 10 here. And by using the tool as MAC-off, he rapidly generates many random source and destination MAC address and IP addresses. Over a short period of time, the switch MAC table fills up. And when the MAC table is full, the switch begins to flood all frames that it receives. As long as MAC-off continues to run, the MAC table remains full and the switch continues to flood all incoming frames out every port associated with VLAN 10. The threat actor now uses packet sniffing software to capture frames from any and all devices connected to the VLAN 10. And if the threat actor stops MAC-off from running or is discovered and stopped, the switch eventually ages back out of older MAC address entries from the table and began to act like a switch again. So it means that the network comes to the naturally. What makes tools as MAC-off so dangerous and that an attacker can create a MAC table overflow attack very quickly? Let's get an example. Let's see that we have a Catalyst 6500 switch that can store up to 132,000 MAC addresses in its MAC address table. And a tool as MAC-off can flood a switch with up to 8,000 box frames per second, creating a MAC address table overflow attack in a matter of few seconds. And this, for example, is it shown here in this output of the macOf command on a Linux host. Another reason why these attack tools are dangerous is because they not only affect the local switch, but they can also affect other connected layer 2 switches. When the MAC address table of a switch is full, it starts flooding out all ports, including those connected to other layer 2 switches, which means that even the other layer 2 switches will be overflooded. To mitigate MAC address table overflow attacks, network administrator must implement the port security. The port security will only allow a specified number of source MAC address to be learned on the port. Port security is further discussed here in this module, where we will explain at the LAN attacks. So now let's go and see all the attacks that we listed at the table, where we learned about layer 2 security threat at the switch attack categories. So let's start first with VLAN hopping attacks. A VLAN hopping attack enables traffic for one VLAN to be seen by another VLAN without the aid of a router. In a basic VLAN hopping attack, the threat actor configures a host to act like a switch to take advantage of the automatic trunking port feature enabled by default on most switch ports. And here we have a threat actor configures the host to spoof VLANs, signaling and Cisco Priority Dynamic Trunking Protocol to trunk with the connection switch. If successful, the switch establishes a trunk link with the host, as it is shown here. Now the threat actor can access all the VLANs of the switch. The threat actor can send and receive traffic of any VLAN, effectively hopping between VLANs. And a threat actor in specific situation could embed a hidden 8021Q tag inside the frame that already has an 8021Q tag. This tag allows the frame to go to a VLAN with that original 8021 tag that is not specified. And here in this slide, we will have an example of double tagging attack. At the first step, the threat actor sends a double tagged 8021Q frame to the switch. The outer header has the VLAN tag of the threat actor, which is the same as the native VLAN of the trunk port. For purpose of this example, we will assume that this is VLAN 10. The inner tag is the victim VLAN here in this example, and it is the VLAN 20. Now the frame arrives on the first switch, which looks at the first 4 bytes at 8021Q tag. The switch sees that the frame is destined for VLAN 10, which is the native VLAN. The switch forwards the packet out of all VLAN ports after stripping the VLAN 10 tag. The frame is not retagged because it is part of the native VLAN. At this point, the VLAN 20 tag is still intact and has not been sent by the first switch. And at the step 3, now the frame arrives at the second switch, which has no knowledge that it was supposed to be for VLAN 10. The native VLAN traffic is not tagged by the sending switch as specified in 8021Q specification. And now the second switch looks only at the inner 8021Q tag that has a threat actor inserted and sees that the frame is designated for VLAN 20, which is the target VLAN. The second switch sends the frame on the target or floats it, depending on whether there is an existing MAC address table entry of the target. A VLAN double tagging attack is unidirectional and works only when the actor is connected to a port residing in the same VLAN as the native VLAN or the trunk port. The idea is that double tagging allows the attacker to send data to hosts or servers on a VLAN that otherwise would be blocked by some type of access control configuration. Presumably, the return traffic will also be permitted. By this, it gives the attacker the ability to communicate with device on the normally blocked VLAN. The VLAN hopping and VLAN double tagging attacks can be prevented by implementing one of the following trunk security guidelines as we discussed previous: by disable trunking on all access port, by disable auto trunking and on trunk links so that trunks must be manually enabled, and we have to be sure that the native VLAN is only used for trunk links. Another way how attackers attack a LAN network is by using the DHCP messages. A DHCP server dynamically provides IP configuration information including IP address, subnet mask, and default gateway, DNS server, and more to the client. A review of the sequence of DHCP message exchange between client and the server, it is shown here in this figure, which means that they can access this information. And there are two types of DHCP attacks that are most common in the LAN attacks. Both of those attacks, which are the DHCP starvation and DHCP snooping, are mitigated by implementing a DHCP snooping. The first attack, which is the DHCP starvation attack, is to create a denial of service for connecting clients. DHCP starvation attacks require an attack tool such as Gobbler. The Gobbler has the ability to look at the entire scope of leasable IP address and tries to lease them all. Specifically, it creates a DHCP discovery messages with bogus MAC addresses. And we have even DHCP spoofing attack, which occurs when a rogue DHCP server is connected to the network and provides false IP configuration parameters to legitimate clients. A rogue server can provide a variety of misleading information as the wrong default gateway, which the rogue server provides an invalid gateway or the IP address of its host to create a man-in-the-middle attack. This may go entirely undetected as the intruder intercepts the data flow through the network. They can give you even a wrong DNS server because they provide an incorrect DNS server address pointing the user to a nefarious website, and they give you even a wrong IP address, because since they provide an invalid IP address, effectively create a denial of service attack on the DHCP client. And here in this slide, we will explain how a DHCP spoofing attacks occur. At the first step, we have the threat actor that connects to the route DHCP server. A threat actor successfully connects a route DHCP server to a switch port on the same subnet and VLANs as the target clients. The goal of the route server is to provide clients with false IP configuration information. And at the step 2, a legitimate clients connect to the network and requires IP configuration parameters. Therefore, the client broadcasts a DHCP discovery request looking for a response from a DHCP server. Both servers will receive the message and respond, which means the route server and the real server, our network server, the legitimate server. And now the legitimate DHCP server responds with valid IP configuration parameters. However, the route server also responds with a DHCP offer containing IP configuration parameters defined by the threat actor. The client will reply to the first offer received. Okay, both they will offer. And now at the step 4 is that the client now we will accept the route DHCP offer because the route offer was received first, and therefore the client broadcasts a DHCP request accepting the IP parameters defined by the threat actor. The legitimate and route server will receive the request. And what will happen? The route server unicasts a reply to the client to acknowledge its request, and the legitimate server will cease communication with the client, which means now the client is communicating with the threat actor. Let's recall that all hosts broadcast ARP requests to determine the MAC address of a host with a particular IPv4 address. This is typically done to discover the MAC address of the default gateway. All hosts on the subnet receive the process of ARP request. The host with the matching IPv4 address is the ARP request sends an ARP reply. According to that, a client is allowed to send an unsolicited ARP request called a gratitude ARP. When a host sends a gratitude ARP, other hosts on the subnet store the MAC address and IPv4 address contained in the gratitude ARP in their ARP tables. The problem is that an attacker can send the gratitude ARP messages containing a spoofed MAC address to a switch, and the switch would update its MAC address table accordingly. Therefore, any host can claim to be the owner of any IP and MAC address combination they choose. In a typical attack, a threat actor can send unsolicited ARP replies to other hosts on the subnet with the MAC address of the threat actor and the IPv4 address of the default gateway. There are many tools available on the internet to create ARP man-in-the-middle attacks, including DS and if, Cain and Abel, Ettercap, Yersinia, and others. IPv6 use Internet Control Message Protocol 6 Neighbor Discovery Protocol for Layer 2 address resolution. And IPv6 includes strategies to mitigate neighbor advertisement spoofing, similar to the way IPv6 prevents a spoofed ARP reply. Here in the slide, we will explain how the ARP spoofing and ARP poisoning happen. At the step 1, each device has an accurate MAC address table with the corrected IPv4 and MAC address for the other devices on the LAN. Okay. At the step, and this is the normal state with converged MAC address table. At the step 2, we have a threat actor which is trying to do the ARP spoofing attack. The threat actor sends two spoofed Gratitude's ARP replies in attempt to replace a router 1 as the default gateway. The first one informs all devices on the LAN that the threat actor MAC address, which is this MAC address, maps to router 1 IPv4 address, which is 10.0.0.1. And secondly, the second one informs all devices on the LAN that the threat actor MAC address maps to the PC1 IPv4 address, which is 10.0.0.11. And now, this is when the ARP poisoning attacks with the man in the middle attack happen, because the router 1 and the PC1 now remove the correct entry for each other MAC address and replace it with the PC2 MAC address. The threat actor has now poisoned the ARP cache of all devices on the subnet. ARP poisoning leads to various man-in-the-middle attack, poisoning a serious security threat to the network. And another way that how a threat actor can attack a LAN network is by address spoofing attack. IP address and MAC addresses can be spoofed for a variety of reasons. The IP address spoofing is when a threat actor hijacks the valid IP address of another device on the subnet or uses a random IP address. The IP address spoofing is difficult to mitigate, especially when it is used inside a subnet in which the IP belongs. MAC address spoofing attacks occurs when the threat actor alters the MAC address of their host to match other known MAC address of a target host. The attacking host then sends a frame through the network with a newly configured MAC address. When the switch receives the frame, it examines the source MAC address. The switch overrides the current MAC address table and assigns the MAC address to the new port, as it is shown here in this figure. It then forwards frame destined to the target host to the attacking host. When the target host sends traffic, the switch will correct the error, realigning the MAC address to the original port. To stop the switch from returning the port assigned to its correct state, the threat actor can create a program or script that will constantly send frame to the switch so that the switch maintains the incorrect or spoofed information. There is no security mechanism at layer 2 that allows switch to verify the source of MAC address, which is what makes it vulnerable to the spoofing. And since we are at the switches, another way that attackers attack the LAN network is by using the spanning tree protocol. Network attackers can manipulate the spanning tree protocol to conduct an attack by spoofing the root bridge and changing the topology of a network. Attackers can make their host appear as root bridges and therefore capture all traffic that D8 switch domain. To conduct a spanning tree protocol manipulation attack, the attacking host broadcasts the spanning tree protocol bridge protocol data unit containing configured and topology changes that will force spanning tree recalculation, as it is shown here in this figure. The bridge protocol data unit sent by the attacking host announce a lower bridge priority in attempt to be elected as the root bridge. And if successful, the attacking host became the root bridge, as it is shown here in this figure. He now can capture a variety of frames that would otherwise not be accessible. The spanning tree protocol attack is mitigated by implementing bridge protocol data unit guard on all access ports. By using this, we will be able to secure our LAN network by spanning tree protocol attacks. And the Cisco Discovery Protocol is a priority layer 2 link discovery protocol. It is enabled on all Cisco devices by default. The Cisco Discovery Protocol can automatically discover other Cisco Discovery Protocol enabled devices and help auto-configure their connection. Network administrators also use Cisco Discovery Protocol to help configure and troubleshoot network devices. The information from the Cisco Discovery Protocol is sent out Cisco Discovery Protocol enabled ports in a periodic time. Encrypted multicast. Cisco Discovery Protocol information includes the IP address of the device, iOS software version, platform capabilities, and the native VLAN. The device receiving these messages updates its Cisco Discovery Protocol database. This information is extremely useful in network troubleshooting. For example, Cisco Discovery Protocol can be used to verify layer 1 and 2 connectivity. If an administrator cannot ping a directly connected interface but still receives Cisco Discovery Protocol information, then the problem is more likely related to the layer 3 configuration. However, the information provided by Cisco Discovery Protocol can also be used by a threat actor to discover network infrastructure vulnerabilities. Here we have a sample in Wireshark capture displays the concept connects of a Cisco Discovery Protocol packet. The attacker is able to identify the Cisco iOS software version used by this device. This allows the attacker to determine whether there are any security vulnerabilities specified to that particular version of iOS. Cisco Discovery Protocol broadcasts are sent encrypted and unauthenticated. Therefore, an attacker could interfere with the network infrastructure by sending crafted Cisco Discovery Protocol frames containing bogus device information to directly connected Cisco devices. To mitigate the exploitation of a Cisco Discovery Protocol, limit the use of Cisco Discovery Protocol on device or port. For example, we have to disable Cisco Discovery Protocol on edge ports that connect to untrusted device. To disable the Cisco Discovery Protocol globally on a device, we use no CDP run as a command in the global configuration mode. To enable that globally again, we can run the CDP run command in the global configuration mode. To disable Cisco Discovery Protocol on a port, we use the no CDP enable command in the interface configuration. And if we want to enable that again, we can use the CDP enable command in the interface configuration mode. And by this, that was all the information about LAN security at the video 2. Thank you for being with us, and if you like the video, share it with your friends. And if you are new to this channel, don't forget to subscribe, and see you to the next session. See you soon.